All right, welcome, Physics 30 students. We're going to go over lesson 17. Just as a brief summary, we're talking about this guy, Hans Christian Oersted. And Hans Christian Oersted, by accident, discovered that when you run an electric current through a wire, it produces a magnetic field around it. All right, and so to determine the direction of the magnetic field, we have to develop some conventions. And these are conventions you need to know. Anything that is negative, electrons, use your left hand. Anything that is positive, protons, alpha particles, use your right hand. Down here in your lesson, you will have these other conventions. Obviously, this is to the right, this is to the left, this is down, this is up. These ones here, this here means out of the board. So this little dot here is coming out of the board, and this one here, it's like watching an arrow come towards you, and this one here is into the board. It's like watching an arrow going away from you. So this is into the board, or into the page, and this is out of the board or out of the page. Okay, and those can apply to magnetic fields, they can apply to electric fields, they can apply to anything really. They're very general conventions. So here is the first hand rule, and the first hand rule, it says, applies to situations involving a straight current carrying wire. So if you have just something like this, pretend this is a wire, and you've got electrons going through it, is going to produce a magnetic field around it, and that magnetic field is circular in nature. So like this is a solenoid. The magnetic field would be circular, just like this solenoid. Okay, and here are the rules for determining the direction of a magnetic field that is created when electrons go through a straight wire. So electrons are moving in a straight path. Your thumb points in the direction of the current flow, and your fingers wrap around the wire in the direction of the magnetic field. So in this first example here, pretty straightforward, you have the current carrying wire shown here. Draw a vector that shows the direction of the magnetic field to the right of the wire. So right here, at this point right here, what is the direction of the magnetic field? The X here means that the electrons are going into the board. So you take your thumb and you point it into the board. You see that? You point your thumb into the board, and which way are your fingers curling? Well, if I point my thumb into the board, like into the camera here, which way are my fingers curling? From my perspective, they're curling in a counterclockwise direction. So in other words, they're going like this, in this direction here. So what's the answer to this question? This is the direction of the magnetic field. In other words, at the top, the direction of the magnetic field is going to the left. Here it's going down. Here it's going to the right. And the answer to the question is up. The magnetic field to the right of the wire is up. All right, so that's the first hand rule. Let's just do another example of that. Let's say I have a wire going this way. And I say the electrons are going in the electron flow going this direction here. So electrons are going through this wire. What is the direction? Let's say I ask you, what is the direction of the magnetic field below the wire? Below the wire. So you're going to take your thumb, your hand, your left hand, because electron flow, you point your thumb in this direction here to the right, and your fingers curl around it. So let's say that this is the wire, your fingers curl around it. At the bottom of the wire, what's the direction of magnetic field? Well, I'm gonna have to curl my fingers around this way, and I can see right there, which way are my fingers pointing? They're pointing out of the board. So the answer to this question, what is the direction of the magnetic field below the wire, would be this. Oops, not this one. Out of the board. If I ask you the question, what is the direction of the magnetic field at the top of the wire, then it looks like this. And obviously my fingers are pointing into the board. So the answer for that one would be this. Okay, what is the direction of the magnetic field behind the wire? Is the wire behind the wire? What is it? Down. Behind the wire is down. What about in front of the wire? In front of the wire looks like this. So it's up. Okay, so hopefully that clears up the first hand rule, which is for straight wires. Now, if you go to the second hand rule, the second hand rule is when you have something like this called a solenoid. And if you take a solenoid, you take a wire and you wrap it in a circular path here, and you do a whole ton of wrapping. So what's going to happen is there are tons of magnetic fields created because there's so much wire here. There's so much more wire here than one straight piece of wire. And these magnetic fields all reinforce themselves, and they end up creating a straight magnetic field. So you've got all these curls here. This is the electron flow. So the electrons are going around and around and around and around this wire. But the magnetic field that it produces is actually straight. Whoops, let's go different color. So it's a straight magnetic field, and with a north pole and a south pole. And this is the way that we determine the direction of the magnetic field when you have a curved wire or a circular wire. And obviously, it's the exact opposite of the straight wire. A straight wire produces a circular magnetic field, and a circular wire produces a straight magnetic field. So they're kind of opposite. But this magnetic field is so much stronger because everything gets reinforced because there's so many coils of wire. There's so much wire producing so much magnetic fields. It's just much stronger. So how do we determine what the rule for the second-hand rule is? That you are going to curl your fingers in the direction of the electron flow, and your thumb points in the direction of the magnetic field, okay, or to the north end of the magnet, because as we all know, magnet is a magnet, north, south. Magnetic field lines always go from the north to the south, from the north to the south. Okay, from the north to the south. So let's do an example of that. La 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 la. There it is. There's a good good diagram on the next page. Oh, there's no examples here. Okay, let's go back and do an example. So let's make an example up for this one. All right, so let's say I have a solenoid here, and I've got a wire curving around it like this. And let's say I run electrons this way. If I run electrons this way, what is the direction of the magnetic field? In other words, where's the north pole of the magnetic field here? Well, I'm going to take my solenoid here, my solenoid. Look in the diagram, you can see the electrons are going up and in front of the solenoid. Up and in front. So they're in front of the solenoid and they're going up. So this is my hand configuration for this example here. And which way is my thumb pointing? To the right. So this will be the north end of the magnetic fields that's created, and that will be the south end. Okay, let's try another one of those. Let's do one oriented this way. And let's say the wire is going like this. And let's say this time I run the electrons in this direction. So now electrons, so here's my solenoid. Now electrons are going to the right and they're behind it. And so this is the configuration for that one. To the right, and behind it. And so my thumb is pointing up. So that's going to be north, the north pole of the magnetic field is created. Okay, one more question that you could be asked is, let's say that you have a solenoid like this, and here's the wire. And we say, let's say that that's the north end of the magnet. That's the north end of the magnetic field's created. And this time the question is, which way are the electrons going? For example, at this point here, this point here with the blue dot, are they going up or are they going down? Okay, and you can use the same principle. Here's your solenoid right here. The north end of the magnetic field is to the left, so I'm going to point my thumb to the left. That's the north end of the direction of the magnetic field, and my fingers are curling up and behind, up and behind. So when the electrons are behind the solenoid there, they're going up. Therefore, in this portion here, behind here, they must be going up, and therefore they're coming down this way here. So this is the direction of the electron flow in this example here. Hopefully you can see that they're going up and behind the solenoid, and they're going up and behind, then they must be coming down when they're in front of it. Okay, so that's the first and the second hand rule. I hope that clears things up. I know these hand rules are really difficult to demonstrate in this way. It would be much better if we were in a class, and I think you'd get a better idea, but hopefully that will clear it up. We're going to go to the third hand rule, but I'm going to make a separate video for that one because that one's the more intense and interesting one, I think. So let's end this. Cheerio. We'll see you in a minute.